Okay, everybody, we're gonna get started. Welcome to Eugene. My name is Diego Melgar. I'm Associate Professor of Geophysics here at the University of Oregon, and I'm the Director of the Cascadia Region Earthquake Science Center. The organizing committee for this meeting, for this journey that we're about to embark on, are Ignacio Sepulveda from San Diego State University, Dan Cox from OSU, and Shubham Ghosh from ImageCat over there. And so we're gonna do a little bit of prep work right now to sort of set the stage for why we're here before we start getting into the program. Good. So first of all, the land that we are on is that of the University of Oregon, which is located on Kalapuya Ilihi, the traditional indigenous homeland of the Kalapuya people. Following treaties between 1851 and 1855, Kalapuya people were dispossessed of their indigenous homeland by the United States government and forcibly removed to the Coast Reservation in Western Oregon. Today, Kalapuya descendants are primarily citizens of the Confederated Tribes of the Grand Ronde and the Confederated Tribes of Siletz Indians, and they continue to make important contributions to the communities, to their communities, to the UO, and to the lands now known as Oregon and to the world. In following the Indigenous Protocol of acknowledging the original people of this land that we occupy, we also extend our respect to the 9 federally recognized Indigenous nations of Oregon, the Burns Paiute tribe, the Confederated Tribes of the Coos, Lower Umpqua and Siuslaw Indians, the Confederated Tribes of the Grand Ronde, the Confederated Tribes of the Siletz Indians, the Confederated Tribes of the Umatilla Indian Reservation, the Confederated Tribes of Warm Springs, the Coquille Indian Tribe, the Cow Creek Band of Umpqua Tribe Indians, and the Klamath Tribes. We extend our respects to the many more tribes who have ancestral connections to this territory, as well as to all other displaced Indigenous peoples who call Oregon their home. There is a code of conduct that you all agreed to, whether you remember that or not, when you submitted an application. You can navigate to that code of conduct. That's also on the handout that you have here. And so if at any point any of you feel like that code of conduct has been breached, or you feel uncomfortable or unsafe, you can let any of the organizing committee know, or any of the Crescent staff that's out there on the desk. Refreshments you found, I gather. Restrooms are around the corner over there. Please feel free to come and go and get a top up on coffee or anything like that as the day progresses. Fire exits are clearly marked. Shake alert is operational in Oregon, so should there be an earthquake that is big enough to issue a WEA, a wireless emergency alert, or whether you have one of the apps on your phone, you're supposed to do what? Drop cover and hold on, not run out of the building right away. We can evacuate after, so please keep that in mind. This meeting is put together jointly by Crescent, that I'll tell you about here in a second, and by the Cascadia COPES Hub. We have representation here from them as well. Crescent is a very new effort. We're exactly a year old as of 2-ish weeks ago. And the goal of Crescent, an NSF-funded center, is to contribute to increasing the earthquake culture and resilience of the Pacific Northwest. And so to that effect, we designed the center with several major activities. Hosting science meetings like this one is one of our major activities. And we organized ourselves around one of these 3 pillars that you see here on the screen. We have a lot of science activities that are run by the Science Planning Committee. This is one of them. Others include putting together cyber infrastructure tools, developing community models like the community velocity model so that people can run ground motion simulations, the community fault model so that we can improve our seismic hazard map, the dynamic earthquakes and tsunamis working group that nominally puts together this meeting is charged with tsunami research, but also benchmarking and validating dynamic rupture models and earthquake cycle models. The coupling, the C3S group, coupling, seismicity, and slow slip are putting together catalogs of slow slip events, machine learning catalogs of all seismicity in the Pacific Northwest, and finally the Cascadia Paleoseismology group, which is targeting mostly coastal paleoseismology to establish past event chronologies of big earthquakes and tsunamis in the region. But we have other things going on. Our partnerships and applications group, whom you'll hear about briefly from Valerie, who's standing there in the back in a second, is in charge of building bridges with practitioners, emergency managers, engineers, and people that have a vested interest in responding and planning for earthquake hazards. And we also have the Geoscience Education and Inclusion Group that has a mandate to improve the makeup and diversity of the geosciences workforce. We are the worst of all the physical sciences when it comes to diversity and representation. In case you didn't know that, we're worse than physics, we're worse than engineering, we're worse than math, worse than computer science. And so we have a lot of work to do. And so we're trying to train, help to train a modern workforce, but then one that also represents the diversity and makeup of the United States population. And they have a number of activities. We also have 4 special interest groups, which we think of as the things we really would have liked to fund as well, but didn't have enough money to also fund. And so those include the liquefaction, landslides, and failure working group, the ground motion modeling working group, a fluids working group working on the fluid budget and subduction zones. And I'm missing one. And the offshore observations, thank you, Jay, working group was tasked with helping to organize the offshore infrastructure that we need to observe at Cascadia. The Cascadia, sorry, and then to tell you more about partnerships and applications, I'll give the microphone over to Valerie here.
Yeah, thanks. Hi, everyone. I'm Valerie Zahakian. I'm a part of CRESCENT, and one of the things that I do inside it is with Andy Clifford, who will be here at lunch today and would love to meet you all. Run the partnerships and applications pillar of CRESCENT. And in the sense, we recognize that there are a lot of different components to improving resilience in the region, and one of them is how we can incorporate new findings from science. CRESCENT is predominantly a science center, so we're mostly focused on science efforts, but in the P&A pillar, we're trying to figure out what are the ways that we can translate that science into resilience in some way. So in thinking about where do we fit in that spectrum of going from science to resilience, but then also in terms of asking organizations, partners, and stakeholders in the region, what kind of science do you need to do your job and improve this resilience? So a lot of this is individual meetings, and we are reaching out to individual agencies and organizations, and we would love to speak with any of you who might be interested. But we're also doing things like we have an annual workshop. Our first one was in June. This is about 100 to 150 people that's mostly focused on partners. So people that are scientists not working in the academic space, state agencies and organizations, emergency management organizations. And we were focused on these topics about how can our science agenda respond to what the hazard community of practice needs. We also have a couple of other more defined programs outside this. So there's the Cascadia Lifelines program is run out of Oregon State University. It's existed before CRESCENT. By mostly Mike Olson, but it's a consortium of engineers, practicing engineers in the region. They do a lot of work in that space, and one of the things that they do is run a webinar. So we're running some collaborative webinars with them over the course of the CRESCENT project and grant that's focused on Cascadia specific science and resilience. And this is an example of one of the seminars. This one was in April from Dr. Shane Brown, but there are a lot of others this year if that's something that's of interest. Okay. Yeah, and I think otherwise I'll leave it at that, and we'll be around at lunch and at the poster session, so please come find us.
Thanks, Valerie. Apologies about the glare. We're not used to sun in Oregon. So if you wait long enough, it'll go away. The other organizing partner for this meeting is the Cascadia COPES Hub. Harold, I'm gonna ask you if anybody has a question, you can go to Harold, please raise your hand to talk about the COPES Hub. They predate CRESCENT by about 18 months, I would say maybe 2 years. And they are also focused on resilience, mostly around coastal hazards, and have a broader mandate than just earthquakes and tsunamis, like CRESCENT does. Their team 1 does earthquakes, landslides, and tsunamis, but also their team 2 works on sea level rise, flooding, erosion, and ecosystem change. And team 3 works on helping communities prepare, respond, and recover from hazards. And team 4 is much like our GI group, works on broadening participation of students in STEM. And then they have CSERC, the community engagement and co-production of coastal hazard knowledge. So if you have any questions, please ask Harold. We're trying to not duplicate efforts, so we're trying to coordinate as much as possible so that the programs that COPES is engaged in are complementary and additive to the programs that CRESCENT is engaged in. And so finally, before I turn over to Ignacio, who's going to set the stage for what we're going to do here, I just want to extend a warm thanks to all the CRESCENT staff that you have been getting emails from, Amanda Erickson and Jill Elizabeth, and Sandy Toms and Andy Clifford. So it takes a lot of work to get 45 people in the same room, as it turns out. And so we're very thankful to them for spending the time to make this happen. Okay, that's it.
Yeah, so thank you everyone for coming. This is almost like a dream for me and Diego when we were thinking to shape this meeting. So I want to talk with you about what is the justification and why we wanted to do this, and why is the long-term desire that we were talking. We started in March thinking about this thing with Diego. So first of all, why we should bother about tsunamis? This is a typical slide I share with my students when we start addressing this problem of the tsunami. And we need to agree that when we have a tsunami, the tsunamis happen with a very low recurrence, right? We are talking about centuries between different tsunamis. But the thing is that if we start to try to come up with an idea, with an order of magnitude of what is the probability to face a tsunami, we can realize that actually the probabilities, the chances are not small. For example, if you just consider your average lifetime, which can be, there I was putting 82 years as an average of the population here in a wealthy country, you can see that actually the chance to experience a 500 return period event is actually 15.2%. That is very high. Try to compare, for example, with the chances to be diagnosed by a important cancer, for example. You can see that the probabilities are high. Okay. And it's not only that, even if you don't buy that actually the chances are high, you need to think that actually the impact of having a tsunami is very high. And actually in those pictures that you can see there, that is Cumberland Bay in Robinson Crusoe Island in Chile. And that was my first exposure of the impacts of a tsunami. The picture that you can see here at the bottom is Juan Fernandez before the tsunami. And the one that you can see there is a picture we took with our team from the University of Valparaiso in Chile, where you can see the effects of a tsunami. The impacts are huge. And indeed, if we start to count the death toll and the property loss that we were having for very important tsunamis in the last decade, in 2000 and in 2004, you can see that actually the costs are very high and the death toll is very high as well. Even sometimes higher than some natural hazard we always are scared about. Okay, so certainly we have to do something about tsunamis. So I wanted to share with you these two sites, which I think are very relevant to the meeting we will have today and tomorrow. So first of all, this is a recent speech from Antonio Guterres from the UN, saying that together let's ensure that people's futures are not swept away by tsunami. Let's build resilience. This is a very recent statement, and certainly he's right. We really need to build resilience, okay? But also I want to show with you another idea, which actually is not coming from me. Actually, this was coming from Gary Choke, who will speak today. We had a meeting last week with Shugo and Diego and Gary Choke. And this is a statement from a Nobel Prize, who was saying the issue here is not so much how sustainable development is defined in principle as how it is measured in practice. So the big problem sometimes we have is that actually we have the models to try to come up with an idea of what is actually the tsunami risk. But typically stakeholders, sometimes they cannot take action in order to create the mitigation. And probably, and the problem may be rely on the problem that probably we don't know how well we can inform about those measures. How we can convince the community so they can take action. How we can convince the community that rather than spend 10 making a house, they should spend 100 because in the long term, that is a better business and a safer business. So in order to do that, we really, and in this meeting probably we will talk about a lot about this, how we can create effective tools so we can inform the communities and stakeholders to take action for tsunamis. There is a lot of science, but also there is a lot of implementation. And that is also the reason why we have a session 4, which is talking about implementation. Okay, so why a meeting? So I like history and I like to read a lot about what we did in the last century and how has been the progress of geophysics, oceanography, and specific on the in the tsunami science area. And what I can see is that, of course, in the last century, in the previous century, we could observe that there were several tsunami events which were very important and which were transforming. Because after that tsunamis, we were learning and we were encouraged to try to do technical developments and scientific developments in order to prepare better for a future tsunami. So all these, of course, I don't have all the tsunamis, but certainly some relevant ones in terms of how that was moving science. Okay, another very important thing is that actually in the last century, in the previous century, also we had several efforts, key efforts, which basically were trying to build new advancement in terms of science, of tsunami science. And some examples are, for example, the 1957 International Geophysical Year that helped in order to share technologies for instrumentation around the world. For example, South America and Chile, they could get tide gauges coming from the US in order to have all a network of tide gauges, and thanks to that, we could measure the 1960 tsunami, for example. So that was a very good effort and a very good organization that I wanted to highlight here. Also, another very important one was the 1965, the creation of the Joint Tsunami Research Effort, led by Gaylord Miller. From there, the creation of PEMEL was set. And PEMEL is a laboratory which actually developed the tsunami model using early warning around the US and around the Pacific, for the Pacific Tsunami Warning Center. Another very important meeting also that I want to highlight here is the 1991 Long Wave Run-Up Workshop, led by Kostas Sinolakis, my advisor Philip Liu, and other tsunami scientists by them. One of the big efforts and something relevant that happened after that event was the development of tsunami models. Actually, here you can see in this picture the first run-up tsunami model created, which was the result, or which was appeared after that workshop in 1990. After that, we started to develop tsunami models, which we use for early warning and tsunami hazard assessment. And of course, after the 2004, also we started to move, for example, in terms of the standard building codes. For example, here we have the ASC 716, which was developed in 2016 to address the problem of tsunami loads in this. So certainly we have done a lot, but still there is a lot to do. And one of the dreams of this meeting is to try to meet everyone from different sectors, from academia, from federal agencies, from academia, in order to try to draw a path of what is possible and what we need for the future. And that is your role in this meeting. So this is coming from Ernest Shackleton, who had a very bad luck doing an exploration to the Antarctic, but this was the newspaper, and I always share this with my students. We need tsunami research for hazardous journeys, small wages, bitter cold, long month of complete darkness, constant danger, safe return doubtful, honor and recognition in case of success. Okay, I promise you that. Okay, so in this meeting, what is the big goal? What we want to do? First of all, we need to identify successful aspect and technical challenge. All of you have an idea about what we miss, what we are doing good. We want to share all those experiences. And finally, we want to visualize a roadmap for improvement. Okay? And to do this, we are dividing the meeting in 4 specific topics. So first, we will talk about geophysics and geology. Second, we will talk about the characterization of the hazard. In specific, we will talk a lot about probabilistic tsunami hazard assessment. Third, we will talk about the design using that information, fragility analysis. And finally, we will talk about this important dimension, which is the implementation. Okay, so Shuarup will share with you some very important information, which you can consider as the initial condition to start this discussion, okay? And this is based on the survey that was created, designed by Shubaru and Ron Eguchi. So, anyway.
Thank you, Ignacio. Good morning, welcome. Great to be here. A great opportunity to be part of this research group. One thing I wanted to start off with is one of the goals of this workshop is really trying to understand how we translate and take all the research and the great innovation that's coming out of the scientific community and connect it to application and implementation and making decisions. So in order to do that, we did a pre-workshop questionnaire. We're calling it a questionnaire in order to avoid some of the challenges that was communicated to us that we cannot call it a survey. But in any case, I think we got great response from the community. We sent it out to the participants here, and I just wanted to share a few key highlights. In fact, 3 of them that kind of identify your priorities as Tsunami researchers, how we see them as being used in decision making, as well as trying to understand what the baseline of the science and research is as of now, so that we can kind of move the needle, so to speak. Can you go on to the next slide, please?
Yeah, I can.
We asked several questions, and thank you for responding. And in the handout, you'll find the results of all the responses, but I just wanted to highlight 2 of them. First of all, this very important question of what is important in terms of decision making, whether it's the probabilistic approach versus the scenario-based approaches. So what you'll find here, in terms of the importance scale goes from 1 to 5, 1 being not very important, and 5 being most important. We found that the respondents felt both scenario and probabilistic modeling approaches are important. So if you look at the 4s and 5s here, you'll see the probabilistic approaches got about 80%, and the scenario actually got 90%. So it's a pretty revealing piece of information that this community feels both scenario-based and probabilistic-based approaches are quite important. The next question result I wanted to present is about the return interval that is most important. This is some interesting outcome here. We see at the lower range, at the 100-year return interval stood out to be the most important amongst this group of respondents. And the other was the other extreme, the 2,500-year. And we'll speak a lot more throughout the meeting why this is, and we'll dig deeper into this kind of critical finding here. But we're not super surprised, but I think the real short term and the real long term seem to stand out in terms of the return intervals. And then finally, the last key highlight I wanted to present was what kind of tools are people in this community are using to access or use tsunami risk modeling outputs. And the public open access, obviously there are lots of open models that are being used to visualize or present the results, came out at the top. This one is kind of it was a multiple choice question, so people selected multiple answers, so the total will not add up to 100. So this was kind of another piece of information we found we should share with the community as we embark on this next couple of days of discussions around tsunami, around the priorities and how we can take the research and kind of connect it with the applications. And as I mentioned, all the survey results are in your handout, so please feel free to take a look at it, raise questions, talk to your colleagues about this particular important outcomes that will kind of guide our discussions over the next couple of days. Thank you.
Okay, so in terms of agenda, just a brief summary of what you already know, because probably you review or may not, because everybody was busy every time before the meetings. But this will be the schedule, okay? For day 1, we will have a review of these 4 sessions that I was discussing in the previous slide, okay? So in each of these sessions, we will have 3 presentations, followed by a roundtable. And in those roundtables, we will discuss some key questions that with the organizers, we think it was important to address, okay? If the discussion diverts to another topic, because that topic is super important, feel free to be flexible, okay? We really want to learn from all of you, okay? And everybody wants to learn from each other. So certainly we can do some modifications, okay? But we have the proposal of some questions. For day two, and I forgot to say, very important, we also will have a presentation of posters, okay? We will have some lightning talks. Some people put a lot of effort making some posters, and we will really see this today. And also, in the afternoon, we will have two sections where we will get exposed to the posters, and also we will have a reception at the end of today, okay? We have a lot of work to do, okay? Okay, for the second day, this will be a shorter day, but what we really want to try to know, or we want to learn, is from successful example of people organizing different topics related with tsunami, different programs, different tsunami models, which actually are exposed to the communities. Okay, so we want to learn about these groups and see what are the successful experience or what we can do better, improve for the future. Okay, so this last slide, I don't know if I have to present it, Diego, or someone else. Okay, so here we have more information, and with this, we finish the first welcome remarks, and we can start moving into the session one. Okay, so in each of these sessions here, we don't have breakout rooms. Everyone will be in the same session because we really want to try to catch all the different perspectives for different problems. Okay, so session one will start now. We are talking about geology and geophysics in this first introduction. The moderator is Diego. And the scribe of Diego is, who is helping us with the scribe? You? Don't remember. Where is the agenda?
I think it's Fabian.
Fabian?
Yes.
Okay. Fabian, come here. We need your help.
You can do it from over there. So we asked a few of you, and I apologize about that when we were thinking about what else haven't we thought of, what could go wrong. And this is something I realized we did not communicate super duper well. So our apologies for that. But we asked a few of you if you could help us keep notes for each of these sessions so that we can memorialize what has happened. And so if you got that, if you got that email, thank you for accepting or to do that. Yeah. Okay, so we're gonna give 20 minutes for each of our first three speakers. Loic, are you in charge of raising the red card that says you have 2 minutes?
I am, and we're already 10 minutes late,
know.
so.
It's okay, we don't take slack into the schedule. Loic will tell you when you have a couple of minutes left.
I'll do the 2-minute warning.
After each talk, we'll have time for one question. And then we'll have the rest of the session to ask questions and have discussion between all of us. So without further ado, our first presenter is Lydia Steisch from the US Geological Survey. You can advance.
Okay. One thing.
Thank you for giving me the opportunity to talk today. I'm excited to start the session off because that means I can just listen for the rest of the time to what everyone else has to say. So one of the internal questions we face in hazard research is how big and how often. So today I'm going to be discussing paleoseismology and how we use it to understand more about earthquake subduction zone or earthquakes on subduction zone systems. Some of the techniques that I'll be talking about are also very applicable to crustal faults as well. And how the element of these scientific topics can improve. Can everyone hear me okay, by the way? Okay, great. To gain a deeper understanding of subduction zone earthquakes or any kind of fault system slip behavior, we really need records that last over multiple earthquake cycles. But this requires sensitive environments that are available to record earthquakes and their associated phenomena. Onshore, in subduction zone systems and offshore, we have many diverse records that span thousands to even over 10,000 years in some cases, like along this Cascadia subduction zone shown here, or also along the Hikurangi margin. These data sets come from a diverse range of earthquake-related phenomena. such as coastal land level change like subsidence and uplift, tsunami inundation, which I'll talk a little bit more focused on later, and also shaking proxies like marine and lacustrine turbidites, landslides, and liquefaction. And these data sets together, along with rupture modeling, can really help us understand more about what are the past characteristics of previous earthquakes, how diverse are they, and therefore what can we expect in the future. So, oops, too far. I first want to describe a little bit about the environments in which these paleoseismic data sets are actually reported, focusing again mainly on subduction zone recorders. Onshore, we have systems of very sensitive tidal wetlands and estuaries that are excellent reporters of decimeter scale intraseismic as well as coseismic deformation and tsunami inundation, shown here. Offshore, seafloor sediment cores show these really coarse debris flow type facies called turbidites that serve as proxies for earthquake ground motion characteristics and have also been used to understand more about the timing and pace of earthquakes along these systems as well. More recently, there's been a lot of work done in lake systems, both coastal and further inland, identifying lacustrine turbidites as another excellent reporter of earthquake sources. And in some cases, these can be used to tease out the variability of different source characteristics, like the difference between crestal events, subduction zone events, and interslab events. Bank successions and sediment cores, like those schematically shown here, in tidal wetlands preserve repeated sequences of organic rich tidal wetland soils, basically marsh peats, during an interseismic period. And in the case of subsidence, these are sharply overlain by tidal muds deposited following coseismic subsidence. To estimate the actual magnitude of elevation change that occurs coseismically, whether it's elevation loss or gain, we analyze the presence, the absence, or the change in sensitive microfossils like diatoms and foraminifera or plant species across these boundaries. When tsunami inundation has occurred in the site, we can also get good recorders of sand sheets or silt sheets further up into the estuary systems, and these can be traced fairly far inland. In terms of how these subsidence estimates and uplift estimates are used, rupture models have used the variability in these magnitudes of coastal elevation to basically tease out the differences in the magnitude, the extent, and the slip style in a single event. And tsunami and sediment transport modelings are starting to use high resolution tsunami sand mapping to a similar effect, and I'll show some examples of that later. But for all of this to work together, we really do need high quality age control. So timing is key to understanding how these events correlate from one site to the next, and estimating the frequency magnitude distribution of damaging events along these systems. In addition, we can use these kind of data sets to establish whether there are potential rupture boundaries along these subduction zone margins, whether they're persistent or ephemeral. So earthquake timing and recurrence often relies on radiocarbon analysis, and there's other geochronologic techniques too that have been useful. But importantly, I want to point out that age uncertainty in these various different techniques and how they've been used over the past decades is highly variable. So in many cases, especially in Cascadia, we have a lot of data sets that are centered around using detrital material that is often deposited prior to an event. And so these little probability distributions here are actually taken from the literature, from samples that are collected from, let's say, a marsh peat, a bulk C14 sample, or from bulk C14 samples from hemipelagic muds underneath turbidites. In these cases, they're giving us important age control, but in many cases, it's a broad maximum age. More recent analysis with a closer eye towards the material actually collected for analysis are able to provide much tighter age constraints on the timing of an event. So one example is Discovery Bay here, where material is taken from above and below the horizon. And they were selecting high quality samples that are in situ earth position plant species, not detrital material. And I was able to really narrow down the uncertainty on events like Discovery Bay event 2. And Lake Ozetta is another example. It's a lake system in Washington state where there's some really high precision age control is able to really define the timing of these past events. But in Cascadia in particular, a lot of the data sets that are in the literature, the abundant ones, do still rely on this broader age constraint. And it allows for uncertainty in whether or not events were full margin, full ruptures of the subduction zone, But it also allows for the possibility that there are multiple large events that are sort of hidden within the age uncertainty that currently exists. So the records that we see in an individual site, importantly, can be generated from different kinds of events, multiple different kinds of events. For example, crustal faults can cause uplift and subsidence. They can also cause tsunamis, and they can also cause turbidites. So by comparing a vast array of different types of paleoseismic proxies to what we expect from specific seismic sources, this is one way in which we can really tease out earthquake timing and tsunami hazards and what their sources are. For example, this is some work from the Hikurangi margin in which Charlotte Pizer and her colleagues worked through a data set going back 7,000 years of various different earthquake proxies. And in this case, they're using the turbidite paleoseismology specifically to tease out the spatial and temporal patterns of past earthquakes. And that's because the crustal data set here is really complicated. So there's quite a lot of fault systems that are offshore and come onshore that can complicate the signal and create a bit of a fragmented record. So in this case, the turbidite data sets were really the hinge point on identifying rupture characteristics and sources. But what Charlotte and others highlight also is importantly the age control and the ability to establish synchronous deposition for these turbidite systems was important for their analysis. Along the Cascadia subduction zone, we have a slightly different picture where the coastal records are in general a bit more reliable reporters of subduction zone events. We do have crustal faults, especially in southern Cascadia, that can complicate the system. But in this case, the issue we're often trying to work with is to decipher which events seem to correlate along strike and maybe full margin events, but which may have also been a serial ruptures that occurred in relatively short succession. A lot of the previous work has been focused both on onshore data sets, but also these wonderful turbidite records as well to help tie together the coastal records. Originally, these have been interpreted to suggest about 19 to 20 full margin ruptures along the Cascadia subduction zone in the past 10,000 years. However, there's a little bit of an issue with the turbidites in Cascadia currently. The sensitivity analysis we performed and published this past year was looking at age control and its sensitivity in these turbidite systems to various different parameters that go into the age calculation at multiple different sites along the subduction zone. And what was found is that currently the radiocarbon ages are far too uncertain to establish meaningful correlation based on the geochronology alone. Specifically, sedimentation rates and marine reservoir corrections are extremely impactful into the age calculation. And these are elements that we just don't know independently well enough in Cascadia to establish really high quality turbidite geochronology. That leaves petrophysical characteristics like magnetic susceptibility and density logs, some I'm showing here, for correlation and establishing synchronous deposition. Turbidite characteristics, however, are shown to be sensitive to variable sediment routing systems, as well as variable ground motion in a single known event. We learned that from the Kaikoura event in New Zealand. And furthermore, some recent work using dynamic time warping from Noren and Minsky this year in GSAB shows how these data sets, correlation between cores that are very closely collected works really well with dynamic time warping technique. We have really good correlation and high metrics of similarity. But as we get further away, these cores are very hard to distinguish which turbidite correlates to the other one and establish especially a unique correlation between these events. So if we focus mainly on terrestrial sites though, along the subduction zone system, what can we learn and what do we see in these data sets? Alan Nelson in 2021 published a paper using a maximum rupture model focusing mainly on terrestrial age control. And they provided some weighting, some probabilistic weighting towards the quality of the material data to find several interesting spatial and temporal trends. One thing they found is that there may be a persistent rupture boundary that was hinted at but not quite established near Nehalem Bank, near the Columbia River, based on this analysis. And they also found that there is an increased frequency in subduction zone events in southern Cascadia, which we knew about, but there's a higher frequency specifically in the past 1.6 thousand years, which was a bit new. Yet even with these correlated full margin events that they're doing with this, focusing mainly on the terrestrial data sets, Some of this, there may be some evidence for serial rupture in these as well. With a careful eye towards spatial and temporal trends, discordant ages might be able to give us a better understanding of how serial events actually, how often they may occur. So towards that end, Rob Witter and colleagues are focusing currently on the penultimate event. So this would be the event that happened before our 1700 earthquake, which is interpreted in this Nelson paper as a full margin event. This is the age control in this diagram that goes into it from multiple different sites. And the little gray probability distribution is the overlap. So it's a relatively narrow range of about 30 years interpreted for this event. However, when you look at the actual age control that goes into it, the span is over 270 years. So by picking this apart, Rob has shown that there's some variability in ages that form both geographic and statistical age groups. And so this potential full margin event could also be 3 individual events, with a northern rupture and a southern rupture that are in relatively close times of periods of time, about 800 years ago, and then another about 750 million years, or sorry, wrong time period, 700 years ago, that would have potentially ruptured the central part of the margin. And so one of the key sites in this is Bradley Lake, located here at Cape Blanco, where there's recording disturbance event 2 and disturbance event disturbance event 3 in both of these central and southern hypothetical ruptures. Disturbance event 2 specifically had evidence for marine inundation in the lake system. Disturbance event 3 did not. So importantly, another thing I want to mention is that all of these, since they have this kind of subsidence signal, is suggesting that there's a great amount of slip. These are magnitude 8 to 8.5 or greater events that would happen fairly over this 270-year time period. The age control uncertainty still doesn't support one hypothesis or another, but I think this is one example where we can show that these age groups can help us understand more about what are the different possibilities and where to spend a little bit more time. Okay, so paleoseismic data is not just about age control, and some of the more cutting edge applications are pairing detailed evidence along certain sites, like along the Salmon River system here, with careful rupture modelings and their expected impact. So this is an example from the Salmon River estuary in central Cascadia, where there's some pretty high resolution mapping of tsunami sands and their relative thicknesses. So all the dots are where locations where there were cores taken. Yellow means that there was tsunami sand identified, and the thickness is shown by the relative size of each of those dots. And so by using this higher resolution mapping, Sean Paul was able to vary the rupture characteristics for about 15 different ruptures, and they also vary tidal stage, Manning's ratio, a whole bunch of different things, to see which data sets actually fit the inundation expected from the Salmon River estuary. And so here's an example of 4 of those many rupture models that they forecasted. And the ones that best fit the actual inundation estimates from the sand deposition was just suggest between about 12 to 16 meters of slip offshore, locally about a meter of subsidence. And they find that at mean high, higher water, these are some of the estimates that best fit the tsunami inundation observations. So more slip is also permissible in some of these models, but the models tend to overestimate the sand thickness and its inland extent. That said, some of the CRESCENT CPAL fieldwork last year in October is also pushing the limits of the sand extent at this very same site. So this is again that map showing the sand extent from previous analysis. And now I'm going to overlay our new observations from the sand extent was previously estimated to be about here, but you can see from all these yellow dots, we continue to find sand the further we went as well. So from these cores, PhD student Mike Priddy is at Virginia Tech is performing high resolution grain size analysis to better understand the sand extent and its abundance in these different cores. And so now this map is showing percentages of sand at some of the samples taken back to the lab. And the yellow dots are suggesting that there's more than 10 to 15% of sand content in these. He and others are also using diatom analysis to better constrain the inundation limits of the 1700 sand. And the initial results I'll show from one of the cores taken right here. And the reason why we're looking at diatoms is because for historic events, we find that diatoms can be transported up to 2 kilometers further inland than sand deposition. So this is a CT scan from that one core that I was showing in red on the other slide, showing a pretty clear transition from marsh peats to tidal sands. And there's a tsunami deposit here. It's very thin. It's perceptible in hand sample. You can feel it, but it's pretty hard to tease out here. But when we look at the tsunami or the diatom abundances and the relative species throughout this core system, we can see a pretty nice transition from earthquake or pre-earthquake marsh type species to post-earthquake tidal flat type species. And in between, there's a mixed assemblage with marine diatoms in them. Many of them are broken at the site too, suggesting high energy incursion at the site. So sand, very important, helpful for mapping, but silt size and smaller size fractions and using diatom analysis can help us bring us closer to the actual inundation limits at some sites like this. So in another, this is a video, I don't know if you can hit play. Oh, 2 minutes, okay.
Yes.
We can actually see that sand inundation goes only so far, but there's silt inundation that can be modeled as well. And so this is some other work from Jean-Paul Lassalle showing that silt inundation is reaching some of those places where we were actually collecting some sands and silts. Okay, so just to review, what do we know? What do we not know? And what do we need to do to know what we don't know? So I hope I've convinced you that a multi-proxy approach to paleoseismology really provides some of the best constraints for identifying rupture sources. Coastal deformation and tsunami sand extents are excellent benchmarks for rupture models, and this paired approach is really ideal. Precise ages really do matter, and we're really trying to work hard on that currently. What do we not know? Well, in many cases, the age uncertainty currently still prohibits us from identifying specific rupture extent and sources. And rupture characteristic variability over time is something that is a relative frontier in at least Cascadia. So what can we do? Well, better age control. I'm always going to be a proponent of that. But specifically, I don't think there's really bad ages. There's just in many cases bad context. And so taking a close eye to what is sampled, how it relates to the earthquake is critical for getting those good ages. High resolution data at more sites, like what's been done at the San River estuary, is ideal. And there's some work at the Pacific Coastal Marine Science Center and the USGS on offshore sites too. So Jenna Hill is working very hard at some really detailed core transects offshore to look at turbidite evidence in many different places, especially southern Cascadia. And more models using paleoseismic data sets as constraints further back in time is also on the frontier. So lastly, I just wanted to show some ongoing field efforts from the USGS, from the COPES Hub folks with us in the field, and CPAL Crescent Group. And so this is field work just open over the past couple of years. There's me jumping on these boards at Wilpa Bay, at the Salmon River Estuary, Coke Heel, and also Lagoon Creek. So these are all sites we're targeting because of good quality evidence for subsidence and tsunami inundation. We're doing higher resolution tsunami sand mapping for the 1700 event at all of these different sites. And we're doing downpour age control for earlier events as well in a couple of those different places. And this is just an example from just last month. Some new cores taken on along the Bone River, extending what we know into an unmapped area and taking some samples for that detailed core analysis. And so with that, maybe I have time for a question.
Diego? Can you mention for the Zoom people to join the Slack as well for questions?
For online?
Yeah.
Yes, we have time for one question, and while somebody's thinking about that question. We also have folks joining us online. We unfortunately have a room that's a certain physical size and weren't able to accommodate everybody. And so for those of you that are joining online, you can join the Slack conversation that should be in your email. We have time for one question for Lydia before we move on to Harold. Ron.
Ron Gucci, I'm chatting. That was a great presentation this year. So if you think about subsidence, which would occur in a large event, and you think about the inundation from a tsunami, it would seem to me that, you know, when you have these events, there could be an exacerbation of how far in you would go. Is there anything that you can say that would help maybe us looking forward, that if we were to have an event, how much further, you know, the inundation might occur because of the subsidence and the flow coming in?
Can you summarize the question for the people online?
Yeah, so to just summarize the question, this was a question about, you know, can we learn about a paired approach with the subsidence and the tsunami inundation to learn more about the inland extent? I would say that yes, there is the ability to do that. I mean, we are able to catalog this subsidence. It happens within minutes of an earthquake. And the tsunami invasion would expectedly go further because you just dropped it down. And so the paired approach specifically with rupture models that include subsidence and sediment transport modeling, those ones like the ones that Sean Polisel did, are basically getting that very question. Because afterwards, we're also getting recovery on a time period that we don't necessarily know. It could be years, it could be decades, it could be centuries of recovery to its pre-earthquake elevation. So yeah, that's a really good question.
Could it be done in real time?
Oh, good question. That's a question for a modeler.
Well, we'll talk about it, Ron. Okay, Harold, you're up. Thank you, Lydia, for that wonderful summary. Next up, next is Harold Tobin from University of Washington. You can walk around. Make yourself happy.
So we'll walk around a little bit. Thanks, everybody, and glad to be here. Harold Tobin. Some of you know me as the director of the Pacific Northwest Seismic Network at UW, but that's sort of half my day job. The other half is as a researcher and focusing heavily on understanding the offshore fault systems and in general faulting conditions in subduction zones. Today I'll focus on Cascadia because we're here for the Crescent Center. I want to emphasize that what I'm going to present today is about understanding the sort of architecture of the mega splay fault system, splay faults that branch from it. It's coming and going on the screen, but I'll just say that I'm going to heavily rely on some work that was led by Suzanne Carbat and from Columbia University, and also the work that has been done in collaboration with Janet Watt at the USGS, and especially I want to highlight two PhD students working with me doing really excellent work, Madeline Lucas, who's here in the back of the room, and Anna Ledexi, and they've done a lot of the work that I'm showing you. We can get it into slideshow mode. Is it not working for some reason?
Non-compliant.
Weird.
I have the slide downloaded.
Yeah, you downloaded that mic.
Yeah.
Okay, something always happens.
Yeah, well, I'll let him do that, and I'll just say, so the paradigm here is we're going to be looking at seismic reflection imaging or other geophysical ways of getting at what the offshore structure actually looks like. And I think conceptually, the point is to use anything we can glean as geological knowledge, geological information, often from geophysical imaging, that helps us put realistic constraints on what the faults actually look like. Modeling is always a trade-off between simplification, obviously, and sort of respecting specific realities. And I think we're going to talk a lot about scenario-based versus more probabilistic or logic tree-based styles of approaches to different tsunami modeling systems. And this is a way of just providing the best constraints we can on what those should be, because what the faults that should be modeled are, and then how to constrain them. It's very odd. I've kind of almost never seen a PowerPoint that wouldn't go into slideshow mode, and it certainly did. Oh, look at that. All right, there you go. So Madeline Lucas and Anna Ledexi, and then some of the other co-authors, and there are many other people who have actually been involved in this work. So this is kind of what I just said. The goal here is to say that source models should be informed by our geological knowledge. We should use geophysical observations and map strain accumulation. I'm going to touch on the geodesy and the elastic strain, although I probably should check with Eric what he was talking about. I won't try to repeat or I won't try to overlap with him too much. He's coming right after me, but to go after fault zone structure. And, we need logic trees and weighting factors, so what's more or less likely to occur. So this will follow on some of what Lydia just kind of highlighted for us about potential variability in past events. So what I'll talk about are three things. Basically, the geometry and nature of the plate interface fault in the zone of locking and likely rupture, evidence for and against, and as you'll see, mostly against a through-going megasplay fault system, the thing that's been mapped from the last slide, the Witter et al. 2013 paper. People just call it a splay fault. Of course, as you'll see, to a person who studies accretionary wedges, there are always lots and lots of splay faults, but there's one that maybe is sort of a more first-order structure. So at least at Nankai, we refer to it as megasplay, so I will here too. And then evidence for slip to the surface instead, perhaps, on numerous active shallow splay faults. And we'll talk about the along strike variability. I'm going to focus a lot on the sort of distinctive region of Cascadia, the zones we just call the landward virgin faulting zone, this kind of arc out here, which is where the plate interface is flattest, and also where the lion's share of the strain accumulation based on geodesy is occurring, and where it has a distinctive sort of fold and thrust belt structure as well. I should say that everything I'll show you pretty much has gone into and informed the work of, some of you are very intimately familiar with this work that's been happening to build new logic trees for probabilistic tsunami hazard assessment. It was just published, what, like a week ago or something by Tsunami. And Jay's been heavily involved in that process, but Matt Sipos and Kellen Wong from University of Victoria did a lot of the work, and they focused, for example, on all these questions about where does rupture actually go, and the work I'll show you informed all of that along the way.
The zoom was not on the right side. Is that good?
Are we good? Okay.
Yeah.
So I won't say too much about this because I suspect that Eric's going to talk about it, but geodetic strain accumulation, there have been various models over the years. These are the ones that are often cited from Schmalzli. They are based on land GPS, and they show lots of locking in the mostly offshore region. There's always been this ambiguity about whether you constrain locking as being zero by the time you get to the trench or being complete by the time you get to the trench, because it's not constrained on land. There actually is now some seafloor geodesy that I don't have to show you today, but is soon to be at least submitted work that suggests that in fact locking goes as far out as we actually have information for in this part of Cascadia. This is Eric's paper from 2021, using that as one potential scenario, and it suggesting locking is really strong specifically in northern Cascadia, in that same zone where the landward divergent faulting system is, perhaps comes only shallower and has a zone where it's much more incomplete, and that's the 0.2 locking, I think, line marked in there. And then again, of course, in southern Cascadia, there's another zone that looks like a big lock patch. So a long strike heterogeneity is already kind of pretty clear in our system from that perspective. I'm not going to touch on this question about shadow zones, although at the end I will say there's a reason why I think we don't need a stress shadow zone to explain locking in the up-dip part. Very recently published paper by Sherrill et al. Kind of comes to some of the same conclusions, that affirms that the down-dip limit of substantial strain accumulation, which is that purple line, or expressed in this probabilistic way, basically that boundary, lies entirely offshore. And that there is a gap between the ETS zone and that 0.2 locking contour. And so that wide patch off Washington, again, is where we want to zoom in and spend some more time looking at. So now I'll talk a little bit about our megathrust model that came out recently in this, I guess in the summer, in the Carbat et al. 2024 paper based on some new seismic reflection imaging I'll introduce you to. But just to say first that, we often use, for very good reasons, very smooth models of what the megathrust looks like. So there's the one that's commonly used, the SLAB 2.0. It has a smooth and simplified surface. It's a continuous surface. It doesn't have much in the way of a long strike variability, except basically just down dip, sort of wider or narrower zones, depending on the dip of the plate interface. But we have all this different kind of evidence, and Lydia just highlighted for us the paleoseismic evidence of a long strike and potentially also down dip variability. The geodesy shows some variability along strike, and geometries in the wedge, the input basement topography, even the convergence rate varies from about 34 millimeters per year to 41 or 2 in the north. So there's big differences in all of those things along strike in Cascadia. So the KC21, or Cascadia Seismic Imaging Experiment 21, was really the first new large-scale marine multi-channel seismic reflection study in several decades in Cascadia, and it's the first one that integrates imaging from as far south as we could get permission to go, which was the Oregon-California border, up to mid-Vancouver Island, and crisscrossed the margin for 40 days with the Langseth vessel shooting multi-channel seismic imaging of what the offshore fault zone structure looks like in the subduction system. So there's a kind of cartoon version of what happens, and of course there's a great deal of data processing to build up to these kind of images in depth of the offshore geologic structure at a kind of unprecedented scale. And so we have better imaging of the plate boundary fault than ever before, and comprehensively for the whole margin, and extending basically up onto the continental shelf. Unfortunately, not always all the way in close to the shoreline, where we'd love to have even more information, mostly because of marine mammals, but a great deal more geophysical data than we've had in the past. And all of this imaging, we're able to image the plate boundary fault, and here's one example from down in here, where that is not at the same place as the top of the igneous downgoing plate crust. Like, it's really important to understand that in general, around the world, when we look at subduction zone systems in the offshore, the identifiable décollement or plate boundary fault is usually in the sediment section, or very close to the top of crust, but still perhaps in the lowermost sediment section. In parts of Cascadia, it extends essentially just coincident with or indistinguishable from the top of igneous crust, but in many other places, there's actually gaps in between, and a décollement is present, and that is the plate boundary fault. And especially since we know the locking is out in the section that's dominated by the sedimentary accretionary wedge, and that's what we have to think about is what that fault zone is. So by identifying these horizons and mapping both the top of crust and the plate boundary fault, Suzanne and the rest of us working together built up a model for that across the whole margin. And this is what it looks like. And again, this is published in Science Advances this year. So top of crust over here, plate interfaced over here. In general, there's some distinctive differences between these models and the more smooth version that went into Slab 2.0 and Pat McCrory's models before that from 2012 and earlier ones as well. It identifies a shallower overall top of crust in parts offshore Washington. You can see some of the depth contours here. This one's depth. This one is the dip. So it's essentially the change in slope of that surface, right? Over here on this side, and the same for these two panels. And then there are places where those are essentially, as I said, coincident with each other, but other places where there is significant shallow sediment underthrusting that eventually steps down to the top of crust. So a big step in the plate interface here, south of about 45 degrees north. And we'll talk about some of the discontinuities that are present in here. And then other places where there's, again, pockets of deep sediment décollements where it looks like sediment subduction is real. And also importantly, that means the fault zone is at a different position than might otherwise be modeled. Along strike, there are previously identified strike slip faults in this margin. A prominent one is in this region, Alvin Canyon Fault. And I won't show you all the seismic reflection imaging, but we can see lateral steps along strike in the fault zone across those faults that cut both the lower plate and into the accretionary wedge. And those lateral steps can be anywhere from 500 meters to 2 kilometers in height, and they're sudden steps. So it means that the fault is segmented in ways that are not captured perhaps by some of the broader modeling. So that's kind of summarized here. Here again is that Slab 2.0 image. The structural breaks in the lower plate come in a few different places that kind of define 4 fault segments. In particular, this one is identified with a very large step associated with that Alvin Canyon fault system and some adjacent ones. These are also identified with some faults in the upper plate system. Not so much for this particular break, but a clear step that's associated with the area where there's sort of an edge of the Silesia block in the inner wedge part of the offshore, and then that steps back. All of this is sedimentary accretionary wedge, underlying again that very large apparent slip patch from the past, and in the geodetic model, because this is entirely sedimentary wedge with no Silesia block. Silesia wraps around as the crescent terrain up here in the Olympic Peninsula region. So geometrically distinct segments bound by faults or tears in the lower plate that also then have influence in the upper plate. The region right around this boundary is also associated with the only real seismicity in the wedge that we see, the suspected seamounts published by Ann Trehu, and then Sue Billick and her students have done some recent work. And a real deficit in locking in that region that suggests that if you want a really prominent segment boundary potential, you'd probably place the most first order one in that region, but some of these others as well. The northern segment is flatter, smoother. Fault conditions are more favorable for large rupture for all the reasons that we've seen in various publications over the years. Okay, so next topic I want to talk about is the role of splay faults. So in a cartoon form, if the mega thrust is there, then this mega splay, or that has been hypothesized, would sit in this position between the kind of inner wedge and outer accretionary wedge along the boundary. It was put into that Witter et al. Work and has been used in a lot of the rupture model scenarios and sort of strong weighting in a lot of logic trees. So what we're looking at is the question of, how likely is this kind of boundary? And at least for this region offshore, this is Gray's Harbor transect kind of line drawing from some of the seismic data. Again, there's an older accretionary wedge, still sedimentary material, Forearc Basin, and then this big landward vergent zone of faulting. All of these are splay faults, not just that, everything's a splay fault. So is there a megasplay? And then how far out towards the front does fast slip go? And what about all the rest of these splay faults? So we'll kind of look at those questions using the new seismic imaging data. Whether there is a through-going splay like the one that's in this scenario is important, right? Various models for inundation use these, these so-called t-shirt size models in Cascadia, and the one called L1, which is used heavily in both Oregon and Washington in scenario-based models, includes that splay fault system. So we're going to take a closer look at that, and this is the work that Madeline Lucas has, and she has submitted a paper recently and has a poster here at the meeting, so you can see more of this, and I'll go quickly through some of the data. But basically, she analyzes all of the lines, north to south, along areas where that's been postulated. Again, that yellow line, or white line, sorry, is the L1 splay fault, and looked at the structural style in the seismic reflection data, the seismic character, and other things, and tried to interpret the structure from the seismic reflection imaging. And there's a lot of detail that you can see on the poster, but basically from north to south, we see different zones where the inner wedge, the outer wedge, and a boundary between the two can be identified as different seismic character. And then you can identify individual fault systems with a lot of detailed interpretation that Maddie has done for all these different areas. And I'm just zooming in on one example. There's obviously lots of lines, but here off the Olympic Peninsula, where this line PDO6 sits, then there are a series of faults that are potentially associated with the region of this boundary between the inner wedge and the outer wedge. Actually, that tracks through way over here where there's clearly no fault directly there, but it's a smooth line that went into the Witter publication, so no fault there, so to speak. But the important observation is that all of these faults are actually covered by 1 to 2 kilometers of undeformed sediment. Those faults are not active faults, they cannot be. Because even as blind faults, they would deform the overlying material as it was being deposited. And so in structural parlance, they're sealed by younger sediments. In some other places, faults are coming to the surface and it's either indeterminate because there's no sealing sediments at all, or there's some evidence of potentially active faulting. And as we transition to the Vancouver part of the margin, we do see some evidence showing up of candidates for a megasplay style structure. So some of these large scale faults do branch to the surface. Here's Vancouver Island. We're looking at some of these lines up here. I'll just skip ahead to say there's a bottom line, and Madeline has produced a really good map of where there are candidate faults, which are in white here, where faults are not present at all, which are the gaps, and there just isn't anything there, or where there are clearly conclusively inactive faults in between. And the bottom line is that most of the Washington margin and Northern Oregon margin doesn't really have any evidence for, okay, thank you, for a megasplay fault type system. No through-going megasplay fault. So we can look at the other faults and say, do they slip co-seismically? So again, what about all the rest of these splay faults that are much further out towards the deformation front? And Anil Leduxi has published a paper this year that basically looks in the KC21 data for evidence of places where the sediments are deformed that overlie these faults. These are small slope basins, and then uses higher resolution seismic data from mostly collected by the USGS and looked for surface break or surface deformation. And in this case, for this particular fault, not only is there evidence of surface deformation in sediments, but also an actual fault scarp in the bathymetry, 13-meter high scarp there. So great evidence for slip rapid enough to create a fault scarp, right? At the very close to the deformation front. What Anna has done is map that out over lots and lots of lines, again, all the way here from basically the whole landward vergent zone up to getting close to the Vancouver Island region. And to cut to the chase, all of this light green are all fault structures that show evidence of recent near surface activity. And by recent, we can't say Holocene because we're not quite at that resolution, but we can say, in the uppermost sediments and therefore tens of thousands of years recently, or of course, much more recent, meaning in any given potential earthquake slip. So previous work has identified, there's the Goldfinger maps and things, but just calls all of this potentially active faults. And now we're really discriminating an active domain, and then importantly, all of the stuff behind it inactive. about 10 to 40 kilometers wide. So I've sort of explained that, so I won't go into these those more detailed examples, but basically the picture that we're seeing is rupture may come up the mega thrust fault, probably not, at least in this central part of Cascadia, branching onto a mega splay fault, but instead translating all of this as a rigid block and then concentrating the deformation into these splay fault systems at the deformation front. And that has potential, of course, for tsunami source, depending on what kind of uplift you can generate by these relatively steeply dipping faults. So inner wedge and inactive domain move as a rigid block. Okay, so that's kind of, to summarize that, patchy evidence for a major megasplay fault. I think tsunami scenarios need at least some rebalancing or reevaluation. That's our argument, and we're publishing the work. Slip likely to occur on multiple shallow splay faults, add to seafloor displacement. And we're using this stuff now to influence some of these modeling discussions that I'd love to hear more about what people think about some of this work. I'm sort of out of time, so I think I'll skip over this argument that I've made in the past, and you can see my AGU presentation this year, but I think there's all kinds of reasons to think the fault is locked all the way to here. Basically, it's hot enough and it's rigid enough to be a frictionally locked fault all the way to the deformation front, which of course is actually buried by 2 to 3 kilometers of sediment out there at the toe. And you can look at temperature profiles for Cascadia. I mean, Roy Heinemann said so all the way back in 1995, and there's no reason to think this is wrong, that it's locked all the way to the deformation front. We don't need that. That's the seismic velocity evidence for lithification. Okay, so seismogenic slip to the deformation front is actually likely. It's likely to go up these shallow splay faults. Here's some of the reasons for that. Locking to the trench, there's no trench, but locking to the deformation front is more likely than not. Slip to the trench, dynamic slip then is extremely likely because it's probably good enough to contribute a lot of energy. So that's the last slide. Key points I've tried to make. The plate interface differs from slab 2, more variable dip, and clear along strike steps suggesting segmentation. North Central Cascadia is locked and loaded. We kind of know that, but most likely all the way to the trench. There is probably not a major through-going megasplay fault. And propagation of multiple splay faults in the outermost part is likely from this analysis that we've done. Maybe the last thing I'll say is just to editorialize, segmentation doesn't mean no earthquakes that rupture multiple segments. We know the Nankai trough history has both earthquakes that stick to one segment and earthquakes that cover many segments. So segmentation is just one factor that doesn't tell us what the next earthquake will do necessarily. Thanks a lot.
One short question.
Short question.
All right, Jake.
Yeah, and the areas, the green areas, inactive, active, do Janet Watt's shallower data overlap with that? You talked with her about whether or not she images those active faults to the surface.
Oh, yeah, so we're actually using the Sparker data of of Janet's team, and Janet's a co-author of this paper, and yes, I mean, all of that is completely consistent. You know, there are a few little postage stamps where they're collecting super high resolution data, so getting bathymetry from ROV or UAV type of work. And I mean, that's the next step, right, is to go all the way to the kind of paleoseismology on the seafloor level to look at these things that are scarp generating and others. And actually, Maddie's working now on strike slip faults in the region as well, using some high resolution bathymetry and high resolution imaging, including this new SVP sub-bottom profiler, which is the key tool for that. Thanks. Yeah.
Okay,
Thank you.
we'll hear from Eric next about geodesy of shallow subduction zone systems and deformation modeling. Eric is an assistant professor at University of New Mexico. Floor yours. Thank you.
Great.
Oh yeah, did Harold take the laser pointer?
No, yeah.
I didn't steal it.
Okay, perfect. So thanks a lot for inviting me here. I think I was asked to sort of talk specifically about this question of locking versus coupling. And for some of you, this is probably a talk you've seen me give before, or at least parts of it. But I think it's really worth spending some time sort of understanding the semantics of those words and really making sure that we're clear when we talk about these things, because they turn out to be really different in important ways. And so I kind of want to sort of surface some models and some ideas to just help you think about what that means and what that difference really represents. So, okay, so here's this figure by Gina Schmalzli. Harold had it in his talk. I think you've probably all seen these two models before, right? Sort of showing this idea that we don't have much ability to know what the value of coupling or locking is at the shallowest part of the trench, especially offshore Washington. There's good arguments why it's probably locked, right? But also in the past, arguments have been made to say that it's probably not locked. And especially this is even more common in other subduction zones worldwide. And so there's been this kind of debate. And I actually really like these models. I think both of them really capture some great essence of the sort of the physics of what we think is going on and really sort of do a great job representing the geodetic data. But the thing that I really disagree with here is the word locking. This is not the locking. This is the kinematic coupling. So I want to sort of really, I'm just going to hammer you with that point. Locking and coupling are not the same. And there's kind of a mistake that's been made in the community over decades that led to this kind of confusion. So here's another model for the Japan subduction zone. And this, you can see this is Tohoku, right? So Japan is kind of on its side. This is Tohoku. They've got zero coupling. They're calling it coupling here, which is slightly better, but still confusing. And they just constrained it to be zero at the trench, right? So this is sort of like the model on the right, in this case, right? And so why would we even imagine that it would be zero coupling, right? This seems maybe like, in retrospect, this is from 2010. This seems like sort of maybe an irresponsible model to have produced, but this was really kind of matching the consensus of what was thought at that time, right? So why did we think that the coupling would be zero there offshore Tohoku? And the reason is coupling, the term comes from seismology. So we have great sort of laboratory studies talking about the frictional properties of faults at the shallow part. We have evidence that there's low microseismicity in that shallowest few kilometers. There's maybe the fault is frictionally stable in that area, right? So there's a lot of evidence building up to sort of suggest that idea. And so this was sort of captured in this term seismic coupling, right? So seismic coupling is a term from Hiro Kanamori dating back to the 70s, and it's basically the fraction of slip that is released seismically on a fault, right? So if a fault slips seismically, it's seismically coupled. If a fault slips aseismically, it's seismically uncoupled. But that doesn't mean that the fault is creeping all the time, right? The fault might be not creeping, and then it does after slip. That would be low seismic coupling, but high kinematic coupling, right? And so this is the sort of the key point that I want to just hit you over the head with again. Kinematic coupling is the slip deficit on the fault. Seismic coupling is the frictional property of the fault. So maybe we should just not use coupling as a word, right? But it's hard. I can't get away from it. I keep trying to sort of do this and I never can do it. So so instead of calling it kinematic coupling, let's call it slip rate deficit. And instead of saying seismic coupling, let's say frictional locking. So frictional locking is telling us something about the frictional properties of the fault, whether it's able to release seismic energy when it slips. And kinematic coupling is telling us not about the frictional properties, just whether the fault is slipping right now or not. And there's many reasons why the fault might not be slipping, even if it's frictionally stable, right? If it doesn't have stress to drive it, it's not going to slip. So that doesn't tell us anything about the friction. So, okay, so then I want to sort of show that where this uncertainty comes from at the trench and maybe what we can do about it a little bit. So this is an idea that we sort of came up with a synthetic test where, let's say the worst case scenario, maybe the fault is frictionally locked all the way to the trench. So that means it's not slipping. In that case, it's easy, right? Frictional locking and kinematic coupling are the same thing. Because they're both complete, fully coupled, fully locked. But if we only have data onshore, so here's our data, here's the models that fit the data. Some of them fit a little bit worse, but statistically, we're not gonna be able to detect that, right? They're all chi-squared of 1. So, so these models are all sort of geodetically indistinguishable, but you can see that they've got totally different predictions for what's happening at the trench, right? Some of them are 0 slip at the trench, some of them are creeping at the plate rate at the trench. So that we would call that 0 coupling, right? And so we can sort of just illustrate that. That's, you know, our uncertainty at the trench is 100%. And that's sort of what was captured by the Schmalz et al. Model, right? So any model at the trench can fit the data, because the geodetic data just has no sensitivity to that part of the fault. But if you think about it, what's actually happening there? So the gradient here, this is reflecting convergence, right? So we've got some active strain accumulation convergence happening, maybe uplift. Offshore, if that model was right, that's predicting extension, right? Near the coastline, we've got 0 slip the plate. The overriding plate is going at the rate of the downgoing plate, but then at the trench, it's suddenly going at the full, it's creeping at the full plate rate. So it's extending. So you would need some sort of normal fault to just sort of extrude that part out. But where is the source of stress for that? There are potentially reasons why we could imagine that to be the case, maybe co-seismically or post-seismically or something, but it's not likely that this is going to happen during the interseismic period for hundreds of years, that it's just going to be sort of sliding out on its own, going uphill, right? What's the source of stress for that? And another way to think about this, just to sort of illustrate, if this is our frictionally locked patch, what's the likelihood that the slip rate is exactly these colors, right? Slip rate of 0 here, slip rate of full plate rate everywhere else. It's going to be something more like this, right? So if you pin part of the fault, then the area around it also can't slip. So this is what we call the stress shadow. And it's just basically saying that when you have a fault, a piece of a fault that's pinned, then it prevents stress from accumulating on the fault around it. And so it just can't slip when there's some sort of gradient. I think this is actually kind of an intuitive result when you start to think about what the stresses and the slip really imply for how the fault behaves interseismically. And it turns out that we can do this kind of analytically. It's a nice simple model. It's just a linear constraint on the stress rates on the fault. And so this is a really easy thing to implement. You already have these matrices. This is basically the strain Green's functions that come out of Okada or whichever Green's functions you're using. So you already have this code to do this, and you just have to implement this as a constraint in the inversion. And so when we do that, what we see is that we go from the red to the blue in terms of the range of models that are acceptable that can fit the data and the constraints. And so now this is capturing some of that physical information that we have. If there's locking here that the geodetic data can sense, then it tells us that the kinematic coupling has to be high near the trench. So there has to be a low slip deficit, or sorry, a high slip deficit, a low slip rate near the trench. Because the geodetic data is sensitive to the fact that there's locking down dip. And so even if this wasn't locked, it still wouldn't be creeping at the plate rate. It would maybe creep at, in this case, up to 20% of the plate rate. That means 80% slip deficit, even if the frictional properties are totally stable. So here's kind of another way to view this. So we can plot these stress rates as seismic coupling, right? So anywhere that the stress rate is positive, that's reflecting accumulation of stress frictionally unstable. So here in this model, I can plot the slip rates and the stress rates next to each other. And I call this one the kinematic coupling and this one the seismic coupling. So in this case, I've got some smoothing. The model looks pretty smooth. If we use less smoothing, you can see that those things, the model in this case, I wouldn't necessarily try to run this by reviewers. There's a lot of reasons why this might not be the best possible model, but it's a model that fits the data, right? And what we can even do is use no smoothing at all. This is a totally unsmoothed geodetic inversion, but the fault is constrained by the stress constraint to not have negative stress rates. And so in this case, what the model wants to do is just have individual patches that are seismically coupled. But if you look at the kinematic coupling, it's high almost everywhere. Right? So this really, I think this helps illustrate the difference. Seismic coupling is telling us where the frictional locking might be, where the seismic radiation sources might come from. But the kinematic coupling is where the slip deficit is. So as kind of, I actually disagree with this model. I think I would prefer to say that maybe the fault is frictionally locked everywhere on the fault, right? So this whole thing should be red, right? But you can construct a model in which you only have a few seismic radiation sources. And they tend to sort of lie along the coastline, except maybe down here, there's something that changes right around 45. So I'd love to talk to Harold more about that structural boundary. There's certainly something that changes in this area, which is kind of interesting. But you know, I think the goal here is to just illustrate the difference between these two, right? Seismic coupling is telling you about the frictional properties, which could be very different from what the slip rate actually is. And if you think about how do we do a tsunami model, if you use this as your input to a dynamic rupture model, you're not going to get much tsunami, right? But is that really reasonable? I think it's, you know, we want to really watch out when we do this because what our stress inputs are to those dynamic rupture models really controls how much of that slip we're getting at the trench. And so I wouldn't necessarily say that this model is the right one to use for those types of dynamic rupture simulations, right? Because it's not going to get you much slip at the trench. And so we need to think really hard about what our input stress rates are in order to drive those dynamic rupture simulations. It's actually really hard to get enough stress at the trench because this area, if there's locking down dip, you're just not going to get much stress. Like if you look at the smooth one, just really even here, we've got really high coupling, you don't get much stress out of the trench because it's essentially being absorbed by the fault down dip. And so it's tough to drive that slip, tough to drive enough stress accumulation at that shallowest part of the fault. So there's really some kind of tricky situation there. If you think about the Gorkha earthquake, that was an earthquake in Nepal that had a significant rupture down dip, very concentrated along that edge of the coupling zone, no slip further up dip. So then maybe you need a few of those before you build up enough stress. So that earthquake transferred a bunch of stress from the down dip portion of the fault onto the up dip portion of the fault. So you need maybe a few of those, and then you'll get a big rupture that goes all the way up to the trench. Something like that. I don't know. It's a really interesting question to think about. How do we get enough stress up at the trench to drive large slip, to drive tsunamis? And I should have put in some slides about that, but maybe it's last week. So, okay. So this is another way. This is sort of my version of the Schmalzi et al. A minimum coupling model and a maximum model. And then just showing the difference between those two. We don't use the stress constraints. We have 100% uncertainty along most parts of the trench, kind of except for down here where the coast gets really close to the megathrust, right? And we have a little bit better sensitivity, right? So this is saying we need offshore data. But actually, if we use the stress constraint, then in these areas that really the geodetic data shows deep coupling, that stress constraint helps us sort of extend our model out to the trench. And then we actually can have pretty good resolution on what the coupling, the kinematic coupling value should be. Isn't telling us about the frictional properties. So, okay. So just to sort of recap that part, this indicates, I think, that you know, we can image the offshore part of the fault with these stress constraints relatively well. And we shouldn't believe models that show zero coupling at the trench. Right? If you ever see a model that has zero coupling at the trench, right up dip of a highly coupled zone like the Gaussian model from Schmalzi et al., we can just categorically say that that's incorrect, I think, right? And so there has to be high coupling up dip where there's frictional locking. Okay, so I wanted to sort of, if I have time, okay, I'm gonna have to rush through this. So just to sort of another application of this idea, just to sort of give an example. Places where we have had earthquakes, the Mentawai patch in Sumatra is really interesting. And it's ruptured in a whole bunch of different earthquakes over the sort of the past couple of decades. And in particular, there's a really interesting 7.2 earthquake that happened right in between these two large rupture areas. And it was kind of neat because we have islands here, so we actually had INSAR data. We have a really great resolution, GPS and INSAR on the islands just directly above this earthquake. And what we can say is that there's these two zones of afterslip, but they significantly overlap with the co-seismic slip area. So the co-seismic slip is the blue contours, and then we can really sort of say we cannot fit the geodetic data if we forbid there from being overlap between these two, right? And so if you want to read Reno's paper, it's really awesome. He goes through a lot of details about this. And I think this actually is what we expect, because there's frictional locking, and then there's the area around it that also isn't slipping. And so when you have a co-seismic rupture on a little isolated patch like that, it's going to rupture out into that stable area as well. So this sort of matches this idea that maybe we have these little isolated asperities, some bigger ones, some smaller ones. When you have a rupture on one of them, it's going to propagate that slip out into that area around it. So if we want to understand the frictional properties of the fault, we have to look at things like this. We have to look at slow slip, we have to look at co-seismic, post-seismic, after slip, where the frictional properties are being probed by varying slip rates on the fault. Interseismically, we don't have much resolution. Here's the interseismic coupling model. You can just see it's high everywhere, right? There's maybe a little weird gap in here. That's actually where the earthquake occurred, somewhere in that low coupling zone. So there's evidence that it might be partially coupled there, but we're never going to be able to resolve those disparities kinematically. It's just not possible, right? If we had perfect INSAR over the entire Cascadia megathrust all the way up to the trench, we would not be able to resolve the disparities. So we need other things. So I think I'm really excited about the structural work. That's the kind of thing, potentially offshore data that can resolve time varying slip, if there is any. If there's not, then we're still stuck, right? If you think about here, we have these GPS. These are basically like offshore GPS because they're kind of 50 kilometers from the trench. They cannot resolve any better than what we can already do in Cascadia, because that stress shadow just smooths out all that kinematic coupling. So, okay, so I'll just recap this point again. Please try to avoid the word coupling, or if you have to use it, at least say kinematic coupling or frictional locking, so that we sort of start to disambiguate those terms. There's good evidence that the kinematic coupling at least has to be high near the trench. We still don't know enough about the frictional properties. That's a really big kind of outstanding question. Thanks.
One question for Eric.
Thank you. Great presentation. Something which came to my mind during Harold's talk, but now using your terminology. Do you think that the seamounts which are present in the Cascadia subduction zone either contribute to the kinematic coupling, to the seismic coupling, or maybe to the segmentation and structural breaks as mentioned before?
Can you repeat the question for the people online?
Sure. Okay, so the question is about whether seamounts, sort of as suggested by different papers and in Harold's talk, whether those contribute to kinematic coupling or seismic coupling, or whether they're more sort of important for the segmentation. That is a really tricky question. I think that there's kind of conflicting evidence in various places. So the case of Sumatra, we have not so much seamounts, but fracture zones that are being subducted. And what we see is low coupling along the fracture zones. So that 7.2 earthquake was actually associated with a fracture zone. And that seems to segment the fault into sort of high coupling on either side, but where you have this roughness in the fault that's coming from a seamount or a fracture zone, that tends to produce lower coupling, lower kinematic coupling. But the frictional properties might just be really heterogeneous in there. So it is a really tricky question, but I think that looking at the structure is actually a great place to start for trying to untangle these questions.
Okay, thanks, Eric. Thank you to all three of our speakers. I'm gonna open it up for general discussion. And so the goal with putting these three folks in front of you was to help you realize that it's complicated. Faults are complicated, subduction zones especially, and while we know a lot more now than we did in 1971 when Hiro Kanamori first used the term seismic coupling, uncertainties remain large, sometimes 100%, it seems. So we wanna, we'll pass the microphone around. If you have a comment or a question, you can direct the question to a speaker. You can make a comment based on your own experience and your own work. Before we do that, these are the questions that we want to talk about. These are just seed questions for you. If there's something else that you want to talk about, feel free to bring it up. In order to get the juices flowing, we're going to give you 2 minutes to turn to your neighbor and talk about this. See if the discussion triggered anything in you that you might think you want to bring up. And at the end of those 2 minutes, we'll see if any of you want to contribute anything. So please take the next 120 seconds to turn to your neighbor, introduce yourself, show them your name badge, and talk about this for a second. So does anybody have anything they want to bring up or that they want to share? Ron, please.
Yeah, I have something, you know, it's frustration. So, you know, I see, these technical discussions, and I think they're very, very informative, especially for a non-seismologist, but an engineer. You know, where what we have to do is we have to take, you know, certain assumptions, scenarios, and actually kind of forecast outcomes, you know, and I think this will be one of the topics that will come later in the day, where you're trying to make decisions, you know, regarding design, you're trying to make decisions regarding investments, and where it all starts is the event. And so, you know, Eric had a great presentation, but, you know, I get a little frustrated because, you know, there could be multiple scenarios that are possible. And sometimes I think that we put these scenarios out there with really thinking about what the impact could be. Because some of these, you know, might have an impact in terms of design. And if you have such an extreme scenario where, you know, the outcome is so devastating, you know, you might deter anybody really thinking about doing something practical and reasonable. If you really haven't, you know, studied this, justified it, and quantified in some way. So the question I have for Eric is, you know, with all these various, you know, locking, unlocking, you know, whatever it is, can we place probability on these different scenarios? You know, are some of them like, you know, 10 to the -3 or maybe? So I would need to have that kind of information in order for me to decide how much sort of, how far I would go in trying to forecast things out. And I have some friends from the insurance industry where that is very, very, very critical. You know, you can't just put out these scenarios or series of events or suites or events that so forth, without having the ability to quantify the actual likelihood or your confidence, you know, in these things occurring. And I really think that, you know, the seismological community really needs to engage, you know, with users and with others, with engineers, to be able to at least understand the decision-making framework that we work in, that, you know, that I believe you guys need to fit into. So there's the frustration.
Thanks, Ron. Before I let Eric answer, I mean, that is sort of where we're trending towards, and that's also the very purpose and essence of this meeting. So thanks for that. Yeah, Eric, which one is right? Can you tell us, please?
Yeah, this is, I mean, obviously one of the really big challenges with geophysics and this, especially the geodesy, is so non-unique that we can construct all these different models that kind of equally explain the data that we have. So I think I would kind of point the question maybe toward Lydia and say, you know, we could use past evidence of events as our best constraint on what's likely or what's possible, right? So if we see events that have occurred in the past, then we know that that's possible, right? And that gives us a great idea of what could happen in the future. So taking some probabilities out of the range of previously observed events, maybe in Cascadia as well as other places around the world, we could say what types of things can occur. I think that would be a great way to start, because the geodesy is never going to tell us, you know, which is more likely. They just all fit the data equally well.
Thanks, Eric. And I think you're gonna see, I'm hoping John and Jay are gonna talk about the Powell Center effort. They're gonna wow you with the complexity of this logic tree that they built, which tries to get at that. If this is the suite of behaviors that are possible, now let's give them some likelihoods and weights. Based sometimes on data, sometimes just on vibes,
Yeah.
but it's an attempt to handle
Can I say
it,
something?
right? Yeah, of course.
Yeah, 'cause so as you know, geophysicist, the first time I ever encountered that messy effort of how do you do the logic tree for PTHA was getting involved in this project this past year with very long interminable meetings, right? And I would say that we came in we came in hot saying, hey, take the megasplay out, you know, that's crazy, we don't like it, we have all this data that shows that it's not an active structure for at least a big chunk of the margin. And Kellen and Matt were like, oh, well, wait a minute, you know, so what I came to understand was, okay, so in the end, the influence is, well, do we downweight that part of the logic tree a little more? And do we upweight some other part, like the rupture all the way to the tip? And that's essentially what has ended up happening is it's affecting. And there's definitely some squint and spit kind of, you know, in how much do you downweight it and how much do you upweight it? We're doing, you know, we're essentially subject matter expert opinion is a big chunk of it. And it's hard to understand how to quantify that in a way that, you know, then the ASCE can say, yeah, this is based on, you know, this particular probabilistic assessment, because some of it is expert opinion. But it's rooted in at least observations, and that's a key.
Can we turn to anything else? I mean, I'd like this, I'd like to talk a little bit about thoughts on what is the science that we're missing. So we picked Lydia and Eric and Harold to sort of run the gamut from field-based geologic observation through offshore multi-million-dollar geophysics to modeling and how people are trying to connect those dots. But that's only one path. There are other paths that maybe we haven't talked about. So does anybody have anything they think we really should be addressing that we really aren't, but we could now based on our advances in both technology and research and science? Yeah.
John Elm, Department of Geology here in Oregon. So just to comment, I'm not sure it's a big picture type question, but it was just related to what Diego was asking in terms of new science. But one of the challenges I've seen, and this was a question I was hoping to ask Lydia in terms of Sean Paul's work down in the Salmon River Estuary, is that we were doing these models, we're using best available data of the landscape as it is today. And landscape as it is today is not necessarily what it was in 1700, it could be quite different. And so we're making assumptions about inundation extents and sand thickness and things like that based on what we're doing today and what we see today in the model. So the challenge is how do we actually back out conditions 300 years ago? And we've attempted to do this. Rob Witter's work down the Bradley Lake attempted to reconstruct the back edge of the sea cliff and assume that the beach was probably close to that. So there's ways to do that, but it's a lot of it is judgment. And so how do we refine those types of methods?
What I was gonna ask, great question. And it's not just the landscape's changed, land use from humans has changed, right? Some rivers were dammed, they're no longer dammed. Some farms are gone, they're no longer there. Yeah, Lydia, this one's for you. Like, how do we deal with the fact that we're modeling the flow over land that it might not be what it was 800, 1500 years ago?
This is literally what our small group is talking about as well. And I mean, there's inherently going to be assumptions as we look back in time on what it was. And I think this also really hits at a critical point of getting at what is the variability, because we have been working a lot on the 1700 event to try and really understand what was it like, and then hoping that, well, I would like sometimes use the term hoping, that all the events are similar almost. And I think that's one of the dangers in looking at recurrence behavior from data sets with limited age control, is that it's, you know, we try to do the best with the best example that we have, and then applying it further back in time where there's just an inherent loss in data is difficult to address. So one of the things I would maybe point to is, you know, maybe as a community, we can assess the probabilities of what do we not know, and be a little bit more careful at, you know, assigning to our expert opinion, what are we missing, and how can we encapsulate that uncertainty in a meaningful way? And probabilistic analyses get at one way of it, but yeah, but embedded in that are also scenario-based models. So for example, like we were talking about, how do you know that sand was deposited and not eroded? Or that, you know, because our models are based on, you know, that what we see is truthful. But yeah, perhaps adding, you know, some kind of uncertainty to like, well, maybe it was gone to the models too. And some sophisticated models are doing that, but yeah, it's definitely an issue ongoing for just the 1700 event and for the back in time.
Since I'm holding the microphone, I'm gonna use that power for a second. I don't know how many of you have ever been to a SciAm Geosciences meeting. I was talking to somebody about that yesterday, the Society of Industrial and Applied Math. And those meetings are mostly about multi-physics modeling of geological things. And what happens at those meetings is amazing. What people can model now is fantastic. And so I think the technology is quickly turning into a place where we'll see landscape evolution models and sediment transport models begin to be coupled. The problem is I never see any geologists at those meetings. And so I think there's still a big chasm. And so people are cranking the handle on these meetings, but these models are never stopping to ask, what does Lydia think about which model is more likely? So I think that's also a very simple way to close that gap, is just by people talking to each other. And so that's also something we're hoping to accomplish. Yeah, please, there in the back. Yep.
Well, maybe I can.
Totally.
Thank you very much. So I am Eric from Oregon State University. I'm coming from Japan. I did my PhD dissertation in tsunami deposits. So what we did there was to try to understand what were the uncertainties in the generation of the paleo tsunami. So we know that we don't know the earthquake. We don't even know what were the conditions of the trench by the time of the paleo tsunami. We don't know what was the paleomorphology by the time of the paleo tsunami. So what we did there was to try to segmentate all the tsunami models into the earthquake generation, tsunami event and modeling, and then the paleomorphology, and finally the post-deposition effects, because we have post-depositional erosion, and then we have compaction, and whatever else you want to think about, the bioturbation, anything, so many things. So we have a lot of sources of uncertainty. So what we tried to do was to try to have some kind of boundaries to evaluate random simulations, like how much of the output of the model, of the hydrodynamic model for sediment transport, would be eroded based on observation. And we then just try to summarize all those uncertainties into one kind of distribution of possible sources for the paleo tsunami. So migrating from the best fit option to a range of possible sources. So that showed us that using a very known paleo tsunami deposit in the Sendai Plain, which is the Jogan paleo tsunami, showed us that we could have not only one earthquake, like the best fit, but we could have a range of 30 or 1,000 earthquakes that were possible related and to the paleo tsunami and varying in location. So we did that using Bayesian approximations. So I think we can have some kind of probabilistic approach to the paleogeological evidence that help us to make it more useful for the assessment of the tsunami hazard in terms of probability. So I think that's.
Thank you for that. I think Robert. Then we're going to.
Yeah, thank you. Everyone advisor Virginia Tech. So we talk about these scenarios that are interrogated with models, right? To see as to whether they represent a reality or not, in what you just described, Eric. but it assumes that the models in and of themselves are correct. And I can tell you that they may not be, because of at the scale at which the deposit occurs might not be the scale at which the target scale the hydrodynamic equations are derived for. And also the sediment transport model might not be correct either. If lots of the sediment transport model that we use, even from Paul, are derived for situations that do not resemble what we've seen. Remember the 2011, the wall that was like the picture with the wall that was this black thing, water that came over. Well, that's not the situation for which the tsunami, for which the sediment transport models were developed. These models are at capacity. The sediment transport models are the sediment transport models are rarely at capacity. The set of equations that you have to use, it's fundamentally different because of turbulence scaling and whatnot. We can go into details there, but that is for me the frustration, if I may order someone too, that we are not enabling ourselves to dig more into the complexities of the physical processes that are taking place. We'd say it's complicated, but complication is different in complexity. And we need to be able to address this more. And I think we are relying too much on the models that exist rather than thinking about what they don't do. And I think they don't do a lot. I've been doing this for a while now, and I've become very self-critical about my own results in the past, that we need to be much more interrogating the theory that comes back, in particular at the time when machine learning and AI enters this field, where we don't know exactly, where we lose a lot of control over what is learned and how it's learned. And in particular, and we're doing fascinating things, for example, trying to model the geologic record or stratigraphic column. And just thinking about that complexity that the column has, I think I came to the conclusion, working with Tina and others, and doing some modeling of stratigraphic columns, that what we see in a geological record is nothing else than one realization of a big Monte Carlo simulation, right? So if you take that, if you take the imperfect models, then we talk about complexity, because there are formal ways of interrogating complexity from mathematics and theoretical physics, and then see how that pains out in understanding the uncertainties that we actually face more correctly and more systematically. That was a long. I'm not usually that long.
Okay.
I'm sorry.
Ron turned this into therapy.
Just remember that Albert Einstein sent his son to study sediment transport, so it's a difficult problem. So we have a question from Slack, but also I wanted to try to scale with my comment, because I also have a question. So I would like to also remind that we are talking about extreme, and I want to repeat what Ron was saying. When we are talking about extremes in a problem, we need to be careful when we are ruling out some possibilities, as what Harold was saying when they were having the meeting about the splay faults. We need to remember that those are extremes, and we are trying to be careful with the extremes. So even we cannot even rule out when we are trying to work on those topics. When we were working with the development of random field for the sleep distribution, similar things that Diego was doing here in 2016, people were saying, okay, but still you have a lot of information. Maybe there are persistency in the kinematic coupling in the faults. But you are not even sure about that, as Lydia was saying. We don't know about persistency, so what we should do. So maybe the future is related how we can try to constrain those probabilistic models. For example, conditional random field, that's what you were trying to do with David a couple of years ago. Okay, so that was my comment. Let me go to a question we have from Slack. Can you unlock this again? Sorry. So we have a question from Brandon Shack. He's saying, great talk, Lydia, Carol, and Eric. What the uncertainties with geodetic data in terms of deciphering whether strain accumulation is also taking place on other faults beside the plate interface? Do most models assume everything is happening on the megathrust? Is there any sensitivity to locking on splay faults? So someone would like to answer? Maybe Eric, you know a lot about inversion and trying to constrain the inversions.
Yeah, so I mean, I think I showed one of the models where I was looking at the seismic coupling or the stress accumulation, as just points kind of along the down dip edge of the locked zone. And that's actually going to be the case kind of regardless of whether we believe that the model is locked all the way up to the trench or whether only sort of the down dip edge is locked and the rest is just kinematically coupled. So the stress accumulation is really heterogeneous and it tends to be concentrated at the down dip edge. So whether there's stress accumulating on those splay faults is a difficult question to answer. I mean, my answer would be that it's kind of not accumulating much regardless of what's going on, because we have that deeper locking that's kind of absorbing all the stress. So you might need it might be like a dynamic process that's going to drive the slip onto those faults. So yeah, it's a difficult problem. I think that geodetically, it's going to be really tough to say anything about those splay faults. There's a separate problem that I've been working on in Bangladesh, where the splay faults and the anticlines it's a megathrust, it's an ocean continent collision zone. We have 10 kilometers of sediment. And so the megathrust is actually at sea level. So that means we can use INSAR. And so there's anticlines there. And I think what we're seeing is there's maybe actually active folding of the anticlines going on interseismically. So that's a kind of a counterpoint. Somehow we're getting stress onto that. So there might be some slip that propagates up onto those. But it's a really tricky question, especially to do this offshore. It would be great to have unlimited seafloor geodetic data. And that's, I think, maybe the only way that we're going to be able to get out and answer those questions offshore.
Well, maybe an NSF program manager is listening in on. I'll add a counterpoint to that. The other question is, even if whether they are or not, they move during an earthquake, do they move with every big earthquake, or do we skip them and they only participate every 4, 5, 6, 7? That's another thing I'd like to know.
Well, an alternative, yeah, I mean, I actually believe that even the shallowest ones, exciting. The shallowest ones are beamed up to space, apparently. No, even the shallowest ones, most likely move co-seismically, but certainly they could be creeping, except Eric told us why they probably couldn't be creeping, and I agree with that. They could also move as afterslip, right? And some people will argue, yeah, no, all you're seeing is stuff that's all afterslip. I think it's unlikely. I think the scarps show it and other things show it, but and there's just a lot of slip. But one other thing to point out though is I mean, Eric's the geodesist, but anything where you show a map like that of coupling has to be resolved onto some plane. So you're choosing, and you could certainly make a plane that includes splay faults that you wouldn't see as a difference that you can actually distinguish in some alternative models, right?
I have a quick one. If we look at Southern Cascadia, where the fault thrust belt comes on shore, these outer wedge splay faults that are now on shore have much longer return periods. So it looks like, if that's an analogy for the rest of the margin, that they may not slip in every earthquake, but that's just an additional.
And all of them don't have to. Yeah, right.
Okay, one last one before we are released for biology and/or coffee breaks. Any last comments or questions? Schubert?
I was waiting for my turn because as the organizer, like you say, we want to hear all the time. So we listen to you, Diego, we talk amongst each other. So it's kind of a collective thought here. I think the most important thing that stuck out of those 3 questions was the urgent need to do something we transfer to practice soon. And based on what you said, given the advance of technology and data modeling, we feel that it takes a long time to come out with these hazard maps. Those are like probably a decade apart. Is there something in between that needs to be factored in as we wait for these releases that the practitioners and the users could use? So if you look at again, I keep pointing to this questionnaire. We have identified some use cases. Can some of these things that we're talking about from the geophysics standpoint can be done more rapidly to inform such decision? Again, this is a comment or a question, but this is something we collectively thought is an important thing that we should discuss as a group here.
Thank you, Shubharu. We're gonna take a 15-minute break. 12-ish, 13-ish minute break until 10:20. At which point we're gonna talk about, okay, so we learned about all this complexity and how much we know we don't know. There are mathematical frameworks to try to deal with that through probabilistic, seismic hazard, and tsunami analysis. So we're gonna try to start to transition into, okay, how does all this complexity and uncertainty actually make it into a hazard estimate before Ron tells us about risk in the afternoon. Okay, thank you everybody for your engagement. See you in 13-ish minutes.